they say such and such, it was growing exponentially. So what are they really saying when they say it's growing exponentially? What is the implication there? Was that really fast, right? That's what, when you hear that phrase, people say, oh, it's growing exponentially really fast. So which one is exponential here? Purple or red? No, so that's what people say, right? Both of them are exponential growth. Both of those are showing exponential growth. So it's not just about it's growing really fast. There's a very precise mathematical thing going on that represents exponential growth. Okay, those are both exponential. What about which one's exponential here? Neither. These are both quadratic. These are both polynomial growth or quadratic growth. Okay, so what's the point? Exponential growth means something very specific mathematically, and that's what we want to understand, what it means. So when you hear exponential growth, after we get done with this module, you know exactly what it means. Okay, so that's what we're after. So while I'm taking attendance, I want you to work on this. Going to be enough. So you can work by yourself, you work together. But anyway, here's the setup. So open the cup, the red in the upper corner. A certain type of cell splits into 4 cells every hour. Initially there are 7 in a particular sample. Answer 1 through 4. So there's starting over on the left, do number 1, and then number 2, and then up here to the right, number 3 and number 4. Okay? In the table, for the y values, use the product notation. If you don't remember what that was from last time, ask someone or look in your notes. We want product notation because that's really what this is all about. And then once you get done with the first 4, then you can start this new thing over here, number 5. Okay? So I'm going to take a roll, and you can work on that. Okay, where's Tanner at? Tanner. Okay, you're up, sir. So our input is x. How did you define the variable x? How did you define it?
X would be initial number of cells.
So x is a certain value? It's just one value?
Yeah.
Number of hours passed? Yeah. So number of hours passed, time elapsed in hours since the initial observation, or since there was 7. You could say since there was 7 cells. Okay? All right. How about output? Who's got a good definition for value y? Who's got a good definition for value y? Should be easy.
Number of cells.
Number of cells. Number of cells. Present. Outputs. Okay? All right, so remember when we define a variable, it's meaning all the values the quantity can take on. And we want to make sure we are specific and that we have units, right? If it's a variable, now it's taking on a number, so it needs to have units, okay? So we got our number of hours and number of cells. Those are our units, okay? So we're going to use product notation here. Who's up here? Let's see. Justin P. Yeah. So tell me about at 0 hours, how many cells? 0 cells? 0 hours. 7. Okay, that should be easy, right? So that's before any time's gone by. So then how do we use product notation to show how many cells there are at 1 hour?
You're going to take 7.
Yep.
Times it by 4.
Yep. You want 7 times 4. Is that right? No?
7 plus 4.
7 plus 4. Dustin.
7 times 4 is 0.
Is that how many you got at 1 or at 0 after 1 hour?
The second one is 7 times 4.
Okay, right, so 7 times 4. Yeah, so with product notation, we don't use any exponents. We're literally writing everything out, so we don't use any exponents. Yeah. 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 Because there's nothing you're multiplying it by. Yeah. You could say 7 times 1 or something like that. But. All right. After 2 hours, product notation for a number of cells after 2 hours. Diana. 7 times 4 times 4. That's it. Okay. After 3 hours, product notation. Yeah. Is it Taylor?
Yeah.
Taylor.
7 times 4 times 4.
Okay, so we look at this. What's happening? What characterizes this growth? Nathan, what characterizes this growth?
Well, it's exponential.
But what does that mean? So we're getting at what does that mean?
The output
Yep.
is times, so it's 7 times 4 to the hour.
Yeah, don't worry about exponents. Just what's happening. How is the number of cells growing? That's what we're asking. How is the number of cells growing?
Cells split into 4 every hour.
Okay.
So it's each of those is split into 4 the next hour. The next hour is split.
Okay, that's what's happening. So then how do... Yeah, Farrah. We're not talking about exponents. Forget about exponents, you guys. I'm just asking, how is the bacteria growing? That's all I'm asking. Gee. You keep adding 4. You keep adding 4 to the number of cells. Is that right? Jonathan in the back. What is it? Multiply. So how are the cells growing?
4 per hour. Multiply by 4 per hour that you have.
Right. Every hour to get the next number of cells, you do what? Multiply by 4. All right, so today's class may seem really easy and obvious, but it's this principle that when we get into all the nuts and bolts of the equations and the graphs, you can't lose sight of this right here. That's where we're going to take the time to go really slow, even though it seems easy. Okay? Because you come to a problem that's kind of complicated and you're stuck, 9 times out of 10, it's going to be about this to get you unstuck. Okay? What we covered today. That's where we're going to take the time. All right, so every single hour, the number of cells does what? It's multiplied by 4. It's 4 times the number of cells it was in the previous hour. Okay, so how do I use product notation? Now I want to do product notation to get the number of cells after 15 hours. Product notation. Is it Naz? Naz. No exponents. Product notation. No exponents. Moises.
7 times 4 times 4, 15 times.
He said 7 times 4 times 4, 15 times. Okay, right. So how do we express that then? Right. In product notation. Where am I here? Yeah. So it's going to be, so we have to do this, but then we have to specify what? No, not again. All right, try again here. So we have to specify, what do we have to say? It's going to be 7 times a bunch of 4s. 15 of them. 15 4s.
Can we do that on homework too?
Yeah, definitely. If it's asking for product notation, you have to do it that way. Unless you want to write out 15 4s. You could also write out 15 4s. Okay? So then what about after T hours? How would you use product notation to show the number of cells after T hours? Product notation, Jackson.
Same thing you did for the last for 15, except that little bracket that you put up there.
Right. And what does it mean? So just tell me what it means.
It means that you're quadrupling the number of cells you have every 2 hours for the first 2 hours.
How many? T 4s. Why? Because if T hours went by, how many times did we multiply by? Just don't know what's going on with this. Okay. Right. So there's T times you multiplied by 4. So by the time you get to the T hour, you've got a string of 4 T 4s multiplied together to get that value. Okay? So we said it. Specifically, how does the sample grow? Someone review that again for us. Specifically, how does the sample grow? Michelle? Yeah. Right, right. So every hour that goes by, the number of cells multiplied by 4. So what is the key operation at work? Is it plus, minus, times, divided by, or power? What's the key operation at work here? Multiplication. We're always multiplying. And what gets multiplied? Does the output get multiplied or the input? I heard input and output. What's getting multiplied? The time elapsed or the number of cells? Output, number of cells. And when you multiply, in this case by 4, to get the number to, you take a number of cells and you multiply it by 4, what do you get? Do you get input or output? So we've got a certain output, we multiply it by 4. What does it give us, an input or an output? Another output, right? Because what's growing exponentially? The output. That's what's growing exponentially. That's what's getting multiplied by 4 to get the next output. It's the number of cells that's growing 4 times as much every hour. Okay? So this is all about multiplication. So now we can talk about exponents. Exponents come into play here because we don't want to write out 15 fours or make a bracket and write 15 fours. We want to do 7 times. So this is the only purpose of the 15, of the exponent, is convenience. That's the only point of this. All right? Exponential functions are not about powers. What are they about? Multiplication. Repeated multiplication, in this case by this number 4. That's what it's about. And so the exponent just is a way to, for convenience, to write out that multiplication of 15 fours multiplied together. Jackson?
So when would exponential, like when would the operating function be exponents? Like what is the key operation of work? When would that be exponents?
I have to think about that. I don't know. So exponent is kind of in a different beast. So you got operations. An exponent is a way of representing multiplication. So
I was just wondering why it's going to list it up there.
Just to see if you go for it. To see if you go for that when really what I'm trying to show you is the realities is about multiplication. Yeah. Okay, good. All right, so now we want a function. So the function comes back to looking at this. After t hours, we know that we have what? T fours. Okay, so we want a function that models this growth. All right, so we'll call it f. What's the input, x or y? X, number of hours. So after x hours, what's happened? We had 7, and we did what after x hours? How many 4s will we have multiplied by after x hours? X of them, right? X of them. And so we can say that is 7 times 4 to the x. Question? Okay, so he wants, is this 21 to the x? 28 to the x. What does that mean? So what does that mean, 28 to the x?
It's the number of hours multiplied by 28. That means that it's going by 28 cells per hour.
Right. This would be every hour you multiply by 28. Yeah, so you realize it yourself. Okay? So it's not the same thing because that's multiplying 28 together x times. We want 4 together x times. Okay. So let's summarize, okay, this idea here. Exponential functions. Here we go. Okay, exponential functions. What are they about? First and foremost, they're about repeated multiplication. Repeated multiplication. Repeated multiplication by the same value over and over again. That's what exponential functions are about. That multiplier has a name. It's very important for us. The name is the growth factor. So what was our growth factor for the cells? Was it 4 or 7? Two choices. The growth factor. Is it 4 or 7? The multiplier was 4, right? That multiplier every hour was 4. So that's what's called the growth factor. And does the growth factor, does it multiply the output or does it multiply the input? Does the growth factor multiply the input or the output? Output, and when you do that, you get another output. The output is what's growing exponentially. It's what's getting multiplied. So you take the last one, multiply it by 4, you get the next one. The growth factor is a multiplier on the output to give the next output. So this is the heart of the matter. Memorize this, understand it. This is what, again, like I said, the whole module comes back to this. The whole module comes back to this, everything we do. So we'll add a lot more elements and we'll talk about different things, but it still always comes back to this is exponential growth. Okay. Is there a question? Anybody have a question? Okay, so what about this one? Number 5. 2 pennies are placed next to a chessboard. You place 6 pennies in the first square. You always place in the next square triple the number of pennies in the previous square, right? The number of pennies in the square, so we'll make it the function g. So the first thing you want to determine is what's the input and what's the output of our function g according to the way this is set up. And then can you write the rule for function g? Okay, so first determine the input and the output of g, and then see if you can write the rule for what formula will give the output that you want. Okay, so let's see how you did. Scott, input and output. Tell me about input and output of this.
The input is like the square number, so square 1, square 2.
So what symbol?
S.
He wants S to be the input. What do you guys think?
Yeah.
Okay? And then, so that's your input, and then what's the whole thing represent? What's the output?
The number of pennies on each square.
Yeah, so G of 12 is equal to?
2 times 3.
Or no, so what does it mean? So just what does it mean? That's okay.
The number of pennies on the 12th square.
That whole expression means the number of pennies on the 12th square, or the output when the input is 12, right? That's the number of pennies in the 12th square. Okay, so let's build it up here. Let's build it and then see if it agrees with what you came up with. So on square number 0, how many? So that's like off the board, right? Square number 1 is 6. Yeah, so yeah, go ahead.
2 times 3.
Yeah, where did that 6 come from? It came from 2 times 3. Good. And so now we go to the second square.
2 times 3 times 3.
Does this agree with the setup? Okay, so let's see. Somebody new. Is this another Taylor here?
Yeah.
Taylor here. What's the growth factor?
That's growing every times by 3.
3. So every single time to get to the next pennies in the next square, you take the pennies on the previous square. Sorry, I don't know what's going on with this today. Let's try this. You take the pennies in the previous square to get the pennies in the next square, and you, what? Multiply by 3. So, product notation for the number of pennies in the 9th square. What would the product notation be? Tell me your name again. Jimmy, tell me. And what is that? So over the top, 9. What do you mean by that? Over the top? 9 threes, right. 9 threes. Okay? Exponential notation of that. Moises.
2 times 3. That's pi.
No, of this one.
2 times 3 is 9 pi.
3 to the 9th means what? Omar, 3 to the 9th. What does it mean?
Is that we're multiplying 3 9 times?
Multiplying 3 9 times, right? Okay, because every square that we advanced, we multiplied by 3. So by the time we get to the 9th square, how many times have we multiplied by 3? 9 times. Question, Adam.
I know that 0 or 0, we have 2 because we have pennies next to it. Is it why are we starting with 2 when our input is 176? That's 6 ways, 6 times.
Because the S is the square number, and we know on the first square there's 6. And that came from tripling those 2 that were off the board. See? The help?
Yes.
So that's what we're calling like the 0th square. We're saying these 2 pennies to start with.
Okay.
Then we triple the first one to get that first square. And then we keep tripling. Sure. Okay, so in the nth square. So this happened all through the first lecture, and then after lecture was done, I tried to make that happen, and it never happened, right? It was perfect. It didn't move at all, and I don't know what's going on. Jeez. God dang it, what is doing that? Trust me, if I try to get it to do this after a lecture, it won't do it. Okay, so let's try this. So n, after n in the nth square, product notation. Let's see. Nicole.
2 times 3 times 3 and that's n times.
2 times 3, and what's n times?
3, well, like 3 n times.
Right. N threes multiplied together. Or take 3 multiplied together n times. Exponential notation for that same one. Troy. 2 times 3 to the n. So now we got what do we want our function to be? G of s What will it be? Kiko. This is what she wants. Agree? Ah, wow, it's doing so great. There we go. That's it. Okay? So the exponent, what? It's just to tell us how many times we multiply the growth factor together. The exponent just tells us how many times we multiply the growth factor together. Any questions on that? Yes, sir.
The first one on 0, you have to 2 to the power, that times x to the power of 0, you have to do that, right?
Well, what would be to the power 0? Would the 2 to be to the power 0? 3. So yeah, if you want, 2 times 3 to the power 0. What is 3 to the 0? Yeah, I'm not going to try it. I'm done with this. No, it's okay. So it's 2 times 3 to the 0, which follows the pattern, and it works to give us 2. Okay, page 131. So you're working on this, it's a school enrollments, okay? But I want to make a change, okay? So instead of, oh, does everyone get there? Okay, 131. Okay, so both schools are showing a decrease in enrollment. Just switch them both to an increase. So it says school 1 there in both. The current enrollment is 1980, and the enrollment is expected to say increase 3% each year. All right, and then North School, the enrollment is expected to increase by 20 students per year. So we'll get to decrease, but we want to make sure we don't want to complicate the issue right now. So make both schools have an increase. South by 3%, north by 20 students per year. And you can just go ahead and start on number 2. Go right to number 2. And the main thing here is to really understand the values in that table. You're building that table and you're understanding those values. That's the main thing. If you got that, you can go on to the next page. But don't rush to the table. The table is the point. Okay? Do you want to be a fractional student? I don't. See, I told you I won't do it now. Just get 3 or 4 full rows in each table. Okay, so once you get down to 3 or 4 or even 5, that's enough. Get at least like 3 or 4 in each table. Okay, we'll start with North. So, what was the enrollment at the time, the starting time? What was the starting enrollment at North? And after 1 year, no, increase, right? I switched it. Increase. Switched that, stood right in front of you and changed the problem, right? So what would the enrollment be? 1780. Okay, let's talk about what was the change in T? 1. What was the change in N? 20. Okay? Next year, what's our change in T? Another 1 increase of 1 year. What happened to the enrollment? Change of enrollment was? So equal changes in the time are resulting in consistent changes of the output. Does that sound familiar? Equal changes in the input are resulting in consistent changes in the output. What is that? Who has learned something this semester? What is that? Constant rate of change. This is constant rate of change. We said this, equal changes in the input result in consistent changes in output. That's constant rate of change. But now we can look at this a different way. What's characterizing the growth then? How is it growing? How is the enrollment growing? 20 people, what per year? What operation is it? Addition, right? We're adding 20. This is additive growth, which is another way of looking at constant rate of change. So when you have constant rate of change, you always add the same number, right? You always add the same number every time you increase the input. You add the same number to the output, or subtract. It could be subtract, okay? That's constant rate. That's still another way to look at constant rate of change, as it's additive growth. Is it exponential growth? No, because we're not multiplying, we're adding 20 every time, and that's constant rate of change. A different type of growth. Okay, what about with south? We started out with, what was it? 1980? And now instead of adding a certain number of students, it says it went up 3%. Okay, so I'm guessing some of you did this. First you found 3% of 1980, right? How do you do that? Multiply by 0.3, right? 0.03, watch out. 0.3 is what percent? 30, okay. Watch out for that. It's an easy mistake. So is that the enrollment the next year? It's just the what? Increase. So we could put that over here, right? 0.03, because it's the increase. Right? So we could put that's the increase. So how do we get the enrollment the next year? Add the ones we had before. So we had the amount from before plus the 3% increase. So now watch this. I'm going to rewrite that by factoring out 1980. If I factor out 1980, what's left here? 1 here. 0.03. Or in other words, it's 1980 times what? 1.03. So multiplying by 1.03 is the same thing as doing this process. Finding 3% and adding it to 1980 is the same as just multiplying by 1.03, because what's the 1 represent? It represents keeping the current enrollment, right? Keeping all the enrollment of and then the 0.03, that's the additional 3%. So by multiplying by 1.03, it does all of that. Okay? And what do you get when you do that? Okay? So now, you can do the same thing. Increase 2039 by 3%, add it to 2039, all the math works out. So again, in order to get, so this is what? This is times 1.03. How can I get then a 3% increase on 2039 and find the new amount? Take that one and times it by 1.03 again. That's going to raise that number by 3% and give you the new total value. What do you get? 2100 or 2101, something like that, something close to that. All right, what kind of growth is this? Why is it exponential? Because we're always multiplying. All right, so what's the growth factor? 1.03. So constant rate of change, additive growth. Exponential rate of change, exponential growth is multiplicative growth. Multiplicative growth by the growth factor. Okay. So what this is showing is this is kind of a new kind of aspect of exponential functions. Is that or exponential growth is a constant percent increase. We're keeping the percent increase constant, 3% each time, which is the same as multiplying by 1.03 each time. So this is constant unit increase, and this is a constant percent increase, which means we multiply by 1.03. Yeah? Are you saying, can you just keep doing it like this? Yeah, you can, but then you never see that's the whole point that this is exponential growth. You multiply by 1.03. That's the point, that it's exponential growth because you have a growth factor. Okay, so quick announcement about homework. So web work is an unknown in the future here. So it's kind of on pause, and we don't know what's going to happen with it. So I posted the next written homework is due Monday in lecture. Okay, so there's a written homework due Monday in lecture, and we'll just We're kind of play it by ear, so just keep watching Blackboard for new assignments.
I got this until like 1980 plus 0.03 multiplied by 1980, but I didn't get how we got like the 1.03.
That's what I worked out here. See down here? Do you understand this right here?
Yeah.
You take 3% and you add it to the original amount. So I factored out 1980. So if I factor out 1980, that leaves 1 and then plus 0.03.
What's this factor out?
These both have a factor of 1980. So I'm pulling out, dividing each by 1980,
So
and then calling it 1980 multiplied by the resulting 1 and 0.03. See, so it's like backwards of the distributive property, right? What's the distributive property? You take the 1980, multiply by that, and then you add it to 1980 multiplied by that. Well, that's exactly what this is, right?
yeah.
So I'm going backwards on the distributive property. I'm undistributing, right? I'm pulling out. So do you see how that thing is equal to this? So then I just added 1 plus 0.03, and that's so this whole expression is the same as multiplying 1980 by 1.03. And we want that because that shows that it's exponential growth. Percent change, constant percent change means constant growth factor. Better? Okay.
Is there a specific way for us to know our grade, or is it just off of what you've posted on? Like